Right, so today we are looking at the enveloping, we're finally going to be looking at the actual enveloping structure of these things that we've been looking at so far. Enveloping bigebra of a Lie algebra. And as always, I should write this down, as always, we have G be our Lie algebra with enveloping algebra U with canonical filtration, the collection of U sub n. Alright, proposition here. That there exists on the algebra U a unique coproduct C making U a bigebra such that the sigma G, that is, I believe this is the canonical injection of G into U, that the elements of G are primitive. I guess in this case it should be the singular since I'm referring to the set. Broadly, primitive. The resulting bigebra of U with its coproduct is co-commutative with a co-unit being the linear form epsilon such that constant term of each x in U is epsilon x of times scaling 1. So essentially epsilon is just returning the constant term, and then we can put it back into U by multiplying by the unit, which this means that the canonical filtration Un of U is compatible with this bigebra structure. And the proof. Well, first off, let x be an element of G. Writing that the C0 of x is going to be defined as sigma of x, so x in u tensor 1 plus 1 tensor sigma of x inside of u tensor u. If x and y are elements of G, then we have that CO of x times CO of y is sigma x. We're essentially just foiling out sigma x tensor 1 plus 1 tensor sigma x times sigma y tensor 1 plus 1 tensor sigma y. So this is going to be the same FOIL structure that we saw earlier. Not equals there, this is a plus, these are the diagonal terms. Sigma x tensor sigma y plus sigma y tensor sigma x, so as before, we have, if you recall last time, we had a similar construction, and we see that the bracket is going to get pushed to the left and right of R1, and the x tensor y and y tensor x are going to cancel each other out when we flip, so we're left with the bracket of COx and COy just being CO of the bracket of x and y. As U is, as the name would imply, universal, there exists a unique unital algebra homomorphism C of U into U tensor U such that C of sigma of x is sigma x. That should be equals, not, it looks kind of like the inclusion symbol. Sigma x tensor 1 plus 1 tensor of our sigma x. Which is, as you see from above, this is our C0 of x. Thus C is unique. And keep in mind this, what they're having here is just our G to U to wherever, and every map G to wherever as above. I guess in this case our whatever is going to be U tensor U. Every map to U filters through a map on U. And we have this as being our C0, so giving this as our C, I think is the idea here. Now for part B, this is for the coassociativity of C. So we're going to let C prime and C double prime be linear mappings of U into U tensor U as C prime is going to consist of applying C and then applying C again on the left. This is going to be the U identity, composite C. And likewise, C double prime, as you can imagine, is going to be the same thing, only applying C a second time on the right. These are unital algebra homomorphisms which are actually going to coincide on our sigma g, since for all A in sigma g, C prime of A is just going to factor out to be A tensor 1 plus 1, essentially A showing up in every possible slot and 1s in the others, which is just going to be C double prime of A, similarly, and then that is actually going to be enough for co-associativity. C is for co-commutativity of C. Let TAF be the automorphism on U tensor U, just being the one that you'd expect for co-commutativity, namely the one that just swaps the order. Then we get that the mappings of TAF on the coproduct and just the coproduct directly of our universal enveloping algebra, mapping them into U tensor U, are unital algebra homomorphisms which coincide on sigma of G. And so, once again, we have everything from sigma of G, and so we're good on that front. I guess I should write here, A is uniqueness of C. And that sigma G is primitive. This one is co-associativity of C. This one is co-commutativity of C. Next is D, which is that epsilon is a co-unit. Just keep in mind that we had that epsilon is the constant term of whatever it's acting on. So D. The mappings of the U identity tensor the co-unit applied to the co-product, and I'm guessing we're going to have it on the other side. Yes, indeed. Doing the co-product and then taking the co-unit of the left-hand side. Which are of u into the tensor product of u and k, or k and u, which are both isomorphic to u. Our unital algebra homomorphisms. Which coincide with the identity in U on our generating sigma of G. Alright, and then finally we have section E, which is the compatibility of the filtration. So we know by definition that U0 is K acting on 1, that UN lies within UN plus 1 for all n, and that we know that U is the union of all UN, and we know that the product of UN and UM lies within UN plus M. Let alpha I for 1 through n be images of G in U. Then we get that C of the product of alpha I from 1 through n, the coproduct, is the product of C of the AI, the coproduct of each individual A, which is the product, which can evaluate this equal to AI tensor 1 plus 1 tensor AI, product across I, which is equal to the sum, first off I from now instead of 1, 0 to n, and we're also summing across alpha in II, which I'm gonna write that out here, where I of I is the set of permutations of 1 through n, which are increasing on both 1 through I and I plus 1 through n, just once again to make sure that it's unique up to the order of the elements on those sections. And then with that in mind, this is the product of A of alpha j, where alpha is our permutation, for j equals 1 through I, tensor the product of A of alpha k, where k is going to be I plus 1 through n. So essentially we're just splitting up our indices of A into two groups of every possible, like however many in one, however in the other, and then going through every permutation, making sure we're not double counting by making the permutation on each half increasing. Now, as U sub n is the k module generated by the products of at most n elements of sigma g. The above formula gives that the filtration of un as before is compatible with the bigebra structure. Of UC, of course. Now, next up, from this we're going to define with the bigebra of above UC is called the enveloping bigebra of the Lie algebra C. Essentially, from our old construction of the universal enveloping algebra of G, we see that this structure is incompatible with a unique cogebra structure such that we essentially can upgrade the universal algebra, the enveloping algebra, from a algebra to a bigebra essentially for free. So yeah, we might as well just do that, right? Then this comes with this is followed with a proposition, which is let E be a bigebra with coproduct of C sub E and let H be a Lie algebra homomorphism of G into, as we saw before, that the primitive elements of E form a Lie algebra. Then the unital algebra homomorphism f of u into e such that essentially this f is f of sigma of x equals h of x for all x in G is a bigebra morphism. So essentially, for H being a morphism of a Lie algebra G into the Lie algebra of the primitive elements of E, we can expand it to an algebra homomorphism of the universal algebra of the Lie algebra G into the bigebra E, kind of preserving that being equal to H when restricted to that copy of G, essentially is what I'm seeing here. So for H being able to the algebra homomorphism of G into primitive elements of E, we can expand it into this bigger bigebra morphism. And the proof we will show that F acting on both sides of the coproduct is equal to the coproduct of E acting on F. We see first off these are two unital algebra homomorphisms ran out of room there of U into E tensor E. So this C on the left, I guess, would be, I'm going to write here subscript U to make it clear where it's coming from, even though it's E is kind of unambiguous as referring to the co-unit of the co-product of U. And we also have for A in sigma of G that F tensor F of C of A is F of A tensor 1 plus 1 tensor F of A, which is going to be CE of F of A, since F of A is going to be inside the primitive elements of E. Similarly, if epsilon E is the co-unit of E, the co-unit of E of F is a unital algebra homomorphism of U into K, which is going to be which is 0 on our copy of G inside of U. And so coincides with epsilon, which I'm guessing is the co-unit of U, which I'm gonna mark there. Thus, from our previous propositions, the mapping from f to the function f into the composition of f with sigma defines a one-to-one correspondence between we have bigebra homomorphisms which in this case are going to be from UG universal algebra of G into E, and our Lie algebra homomorphisms of G into the primitive elements of E. And this comes with an immediate corollary. Which is we're going to let G1 and G2 be Lie algebras. With enveloping bigebras a minute there, enveloping bigebras U of Gi and canonical mappings sigma I, each sending our Gi into its universal algebra, bigebra now, sorry. For every Lie algebra homomorphism H sending G1 into G2, we see that the unital algebra homomorphism which we can write as the universal of H from, of course, UG1 into, not Gi, from UG1 into UG2, such that U of H composed with sigma 1 is equal to sigma 2 composed with H, and this unital algebra homomorphism is a bigebra morphism, not just a algebra. And the next chapter, I went through this kind of slow because the next chapter is on the structure of the cogebra in characteristic 0. And that one's going to be both long and intense, and so I think I went kind of slow on this one, so I could call it here with just this one chapter. Yeah, the next video is going to be scary, I think, so look forward to that.